Greetings, welcome to another video. I ended the last video saying, I think I'll get the next video out to you real soon. And so famous last words. So I'll just talk at you for a bit, kind of summarizing what was going on. I did do a lot of work. I actually recorded some stuff, but I don't, there's not really, I don't need to show every negative study. So to make a long story short, everything that I did made things worse, which kind of surprised me. So let's just review again, 30,000 foot view, and then we'll try and go down quickly. And then I'm going to gather some data and try to put together something useful before doing too much more basic research. So to summarize, I started off with this core here. I had some more wines on the primary, but this was it, and it's just in ungapped, two ungapped E-cores. And just on a lark, I was like, okay, well, let's look at some of this bitoroidal stuff where you have two different flux paths, where the secondary can flow on a different flux path. And Thane Hines has done a lot of, out of Canada, has done a lot of work with this, and he generally uses two different materials, from what I understand, so that you have a higher permeability, magnetic permeability flux path on the outside than you have for the primary. And so I looked at this, and I did notice when you load one of the secondaries, you get more out of the other secondary, indicating flux is flowing around the outside. And also, when you have the Arduino, you can get fine control of the timing, which has proven to be important. And what was the breakthrough on this one was when I put a little piece of masking tape between here and there to provide a little bit of a gap. And then I started to get some interesting results with that. So from there, I graduated to something more like this, which is a little bit bigger E-core. And if you can see there, there's about a 1 millimeter air gap, somewhere around there, set up for you, so you don't bother with the masking tape. Which also, if you put too much masking tape, you got to worry about are these snug between here and there. And it worked about the same as that with the masking tape. Maybe a tiny bit better, but not a big improvement. So then I went to, and this is things I've been working on here, is winding some of these. Here's a larger one. I just have an assortment of these, and one of the goals today is going to be to pick one. So here's one, about the same air gap. However, if we go with this secondary, and you'll notice this is 26 gauge instead of 22 gauge, so more on the, that's another variable there, is the turns ratio. Now we're back to no air gap. Or if you go, let's say this one, which many fewer winds there, and we have a pretty large air gap. And at this point it started to be a little bit worse, but I wasn't sure, is it what the difference with the windings or the difference with the air gap. So one of the things, let me put this, well actually let me use the other one. So one of the things I was looking at, that I'm not gonna I won't show you all the video with it. What if you had a setup like this? Now, just pretend there's no wire on there. Pretend there's really, just pretend there's no wire on there. So now you have a primary that's magnetically coupled, but there's like no closed magnetic flux path here. There's like an infinite air gap. And I thought that would work well. I thought you're not going to get much deformation here, because it'll get into here, and then this is a cul-de-sac. The problem that I ran into, and it was so bad, I've done it twice, I might even do it a third time just to make sure I didn't have a wire wrong somewhere. It's true that when you have this set up and you load these, the deformation is almost unnoticeable on the primary, the deformation of the oscillation of the LC tank circuit. But if you're using this as the primary, yeah, I'm just making these up, but it's the ballpark idea, then let's say you're getting a volt out of each of your secondaries. With this, you're getting like 1/10 or 2/10 of a volt out. So I really don't understand that. I don't know why that is, because I mean, so another way, like another way to visualize is, you know, consider this as the primary. So you could have it like that, or you could, if you have it like that, and then you like straighten this thing out. I mean, you would just have a ferrite rod coming into here, and then your secondaries. And I mean, my understanding is you can take a ferrite rod and say, you know, here's your primary, here's your secondary, and it works okay. I mean, I don't see that all that often, but I don't know why you wouldn't get a good transfer of magnetic flux, and I'm just not seeing it. So I don't know what's going on with that. But it's like, okay, back up, forget about it. So I had beginner's luck, I think is the answer there. And you know, it's fun to think about, well, I'm gonna go, oh, where is it? I'm working on this. This is a nanocrystalline core, and so, you know, it'll be fun to go to different materials and whatnot, but it's like, no, let's try and go along with the thing that I had some beginner's luck with and see if I can get something at least modestly useful. So the goal is just sort of to pick an arrangement of what I'm going to use for the primary and the secondary in an inner core. It wouldn't surprise me if just this one that I've had for a while turns out to work as well or better than any of the others, but I'll get started on that. And I will mention there were some like simple things related to timing, and not even like making the capacitor smaller or something like that, but just some like simple sort of obvious things that I had overlooked before that I was seeing do make a difference. So we'll discuss those as we move along here, but let's start with this one, and if this one works well, just run with it. We'll start off where the efficiency probably won't be that great initially, and then we'll make changes that will gradually improve it. So this is the circuit that I built for you in the last video, and the only difference from the last video is I've also added a switch there and a switch there, and their purpose is you're going to be gathering stuff off of the secondaries, and you might want to get rid of that after a set amount of time so that, you know, it doesn't go too high in voltage, and just so that you can make standardized comparisons. And not to rehash all of this, but what you're doing is you're taking the cap and you're charging it from the bus lines, and then you have your primary goes to one leg of the cap, the secondary goes to one leg of this switch. When that switch turns on, the connection's made to the other leg of the cap. The cap discharges through the inductor, so you have an LC tank circuit, and because you have an LC tank circuit, this cap will discharge, and then it'll go negative, and to zero, and then positive, and it will ring back and forth, and depending on how good the Q factor is will determine how long the cap rings. So the nice thing about this setup is, for the cost of a couple extra switches, what you do is, instead of having the cap go negative and then as far back positive as it will go, you let the cap go negative, and then when it's negative is when you shut everything off, when it goes as negative as it's going to get, and then you charge the cap negative and you discharge it the opposite way and it'll go positive. And because you don't have a perfect Q factor, then it's going to go further negative than it will go as far back positive. So in other words, maybe this will go from 10 to -8 to +7 to -6. And so now you can catch it at the -8 and just put in 2 volts instead of catching it at the +7 and having to put in 3 volts. And, of course, when you're running it, this will be here, and your secondaries, the secondary lines will go to this bridge rectifier and the other full wave bridge rectifier, and so that's where you'll gather your output out and see what you get. So let's just go step by step, make sure everything's working. Slow and steady wins the race. So we're at 2 volts, and we're just discharging the cap through here and then charging it again. And what do we see it doing? It goes up to 2 volts, discharges, and then charges the opposite way and discharges. So that's what we want. So the next thing we want to do is to figure out the inductance of this coil, which if it's just sitting there like that, we have a reading of 1.91. But if we put this on here, then you now have a complete magnetic flux path through that tiny air gap. And let's make sure those are where we want them. And we're seeing 6.23. Or after I line it up a little bit better, 6.34 millihenries. So let's jot that down in our spreadsheet, 6.34. So when we put that in, we see that after that many milliseconds, or 791 microseconds, is the place where this cap should be most negative. So nothing is loaded yet, but we've gone up to 10 volts here, and we discharge it for the time where it goes most negative. So here we're charging it up to -10, and then it swings back just about to 9. Charge it up to 10, swings back just about to -9. Charge it up to -10. So we're putting in about 1 volt in order to get back to the initial condition. Now, when we start to load it, there'll be some deformation of that. The Q factor will be worsened, if worsened is even a word. But that's the game here, is that you want to preserve as much of that swing of the cap as you can while getting as much off the secondaries as you can. And there's just a lot of variables going on, but as I said, through dumb luck, I had something that's not too shabby. So now let's hook up the secondaries. Okay, so now let's just hook up one of the secondaries. The workspace is starting to get a little busier, so I'm taping things down. But we have the first secondary hooked up, and what we see, it's at 0. Now this charges up 0.9, and then flings back the other way, 1.3, and then we discharge it. And you'll notice that it's not making it all the way back to 9, but it's still, it's doing pretty well. Now what we're going to do is hook up the other secondary. I know I've showed this plenty of times before, but I'll show it again. And this is how you know that you have something interesting going on. So this is with only one secondary, and we see, it gets to there with the 2 things. Now I'm gonna put in the other wire, and okay, and now we're getting 2.89 out of there, and so we're getting more than twice as much out, and we're also, I haven't hooked the meter up, but we're also getting the same out of here, so like 4 times as much. And that's how you know that some of the magnetic flux is recycling in a beneficial way instead of all of the Lenz law interaction going here. But because this is just same material cores, we also have a much greater dampening. It's not getting back towards 10 anymore, or 9 was where it was at. But it's still doing okay, and we got 4 times out more there. So what we're going to do now is we're going to load it, and we're going to figure out efficiency. So what I've done here now is put a 100 ohm resistor across each of the meters, so there's a 100 ohm load across each of the cap outputs there. Now I've seen that this thing in the past generally worked a good bit better with a higher resistance load. So as I said, we'll start off with what is not the best setup and just see how much we can improve things in different ways. Now that we have this, we can calculate milliwatts out and milliwatts in, and I went over this in some considerable detail in the video sometime back, running the bitoroidal transformer the first time I did this. But just to try to recap that briefly, you know the resistance here, we'll know what voltage shows up. Ohm's law, V equals IR, I equals V divided by R. We know the resistance, we know the voltage, we can calculate the amps. So now you have the volts and the amps, and volts times amps is watts. So that's your watts out, one from one side, one from the other side, and add them both together, you get your watts out. The watts in is a little bit more complicated, but not difficult to understand. We know that we're going to have this thing going from, say, 10, let's say, to 5, and then you're going and putting 5 volts back in. So you're putting 5 volts into a cap of known size, say these are 10 microfarads. So you know the capacitance, you know the voltage. So charge in a capacitor is defined as capacitance times voltage. So, 5 times the 10 microfarads. Amps are, of course, also defined as flow of charge per second. So flow of coulombs of charge per second. And from here how many times in a second, once you add up all the timing, how many times in a second you threw the voltage into the cap and it discharged. So you know how many coulombs of charge are flowing per second. So you have amps, and you also know if you had to put 5 volts in, you have your voltage. So then you have your milliwatts in. So again, not difficult to understand. If you know the voltage change that you made in a cap of a set size, you know how many times you discharge the cap per second, you know how many, the amps that flowed, and the milliwatts that flowed. So let's just run this thing first and see if we're in the ballpark. That's what I'm looking for here, just in the ballpark. And then there are some changes that I'm going to try. Okay, so just as the very first thing, we're just running it here, and it flips back to 6.8 something, 86, and we're getting that voltage out from one, that voltage out from the other. So when we put that in the spreadsheet, it's just the first one here. There's your total milliwatts out, and that's your total milliwatts in, and so that's your efficiency. So it kind of stinks, is for whatever reason, and I don't know how it happens, but the loaded and unloaded resonant frequencies are different. So in other words, we should be able to find a spot where this swings back a little bit better and we don't lose much off of the secondaries. And so we kind of have to poke around for it. So what we do, come on. If we go down to the bottom here, we run it once, and then we take the on time and decrement it by 10, and then run it again, and we're looking for what's the best spot with this load for this. Okay, forgive me, I had forgot to update the timing for calculating the watts in the first time. So I got rid of everything else, and it charges for 400 microseconds and 200 off, and then the on time, which was 820, and then 200 off, and then it does it a second time there. So if we charge that, sum that, you have that many microseconds. So every 1620 microseconds you charge the cap, and so we put that in there, and there's your frequency, and we calculate watts in again. And so that is actually watts out, watts in efficiency. So better, and now we have an easy way to keep track of this. But let me go back to fishing around for the best frequency, the best on time. So after fishing around, I found the best timing is in the ballpark of 700 microseconds as opposed to the calculated 791 for this particular load. And when we run it here, let me recompile. Now when we run it, we see this flipping instead of 6.8, whatever it was, back to about 7.31. And this is what we're getting out from our secondaries. So let us now put that in the spreadsheet. So we're actually getting a teeny tiny bit less out from the secondaries, and we're going a little bit faster, so that's all bad. But the big thing is, instead of going from 10 to 6.86, we're going from 10 to 7.31. And when we put that in, now that's our milliwatts in, and that's our milliwatts out, and that's the efficiency. So the easiest thing to do is to go up on voltage, but before we do that, there's another thing that I want to check out, which I think will work. So one thing that occurred to me is we're charging the capacitor for 400 microseconds. Now let's just, pretend we charge it for like 4 seconds. The whole time that's charging, you have a 100 ohm load across the secondary, and the secondaries are just discharging. So in other words, you want to discharge this thing as soon as it's charged up, because otherwise you're just wasting voltage across your resistor. So is that too long? And I think we can get away with going a little faster. If we go over to, I love DigiKey, here's their calculator for this. If you say you have 10 UF and the resistance is going to be 1 ohm or less across your solid state relay, so the time constant, you want 5 time constants for full charge. The time constant is that, so we want 5 of those. This we got it times by 1,000,000. So what do we got here? 0.1, 2, 3, 4, 1 times 1, 1, 2, 3, 1, 2, 3 equals 10 microseconds. Now we got to times that by 5 for full charge, so you'd need about 50 microseconds. Now you also have to factor in how long it's going to take the switch to turn on, which supposedly is like 200, but if you leave the resistors out, then you're hitting it with a lot more current, and so it's probably like 50 or 100 microseconds to turn on. So you could probably get away with 100 to 150 microseconds of charge time and still get a full charge. We're at 400, so let's just first drop it to 300 and then see if we can get away with 200, but see if that makes things better or worse. So we can see that things still swinging back to 7.32, 7.34. Now we're getting 1.78 out from 1 and 1.44 as compared to 7.1 and 3.9, but it's going a little faster, so we have to change that 400 to a 300, put in the new numbers and see what it all calculates out to. Okay, so it did make better. That's now milliwatts in, milliwatts out, and the ratio. Let's see if we can get away with 200. I don't think we can go faster than that, but we might be able to get away with 200 and still have the cap charging fully. So now I've gone to 200. We're getting still more out from each of the secondaries, and I'm realizing that this cap is draining out as well when nothing is going on, so we're seeing this looks a little bit better too. So let's put those numbers in. Okay, so when we put those numbers in, now that's our ratio. The next efficiency improvement here at 10 volts will be, what about the off time for the switches? So let me shut that down. If we go back here, now we could, you know, if you put it on the oscilloscope, you could see if it's still plateauing. You might be able to go even a little bit faster, but that's enough now. I mean, that was a fairly significant improvement. Now you have the off time where the switches turn off, and I put each of those at 200 microseconds. Now if we go, this is for the Comas AC37. The typical off time is 50 microseconds, but it might be as long as 500. So I had it at 200, but it sure would be nice to take it down to 150. I'm not going to go all the way down to that because you don't want the thing stepping on its toes. Now for the other ones, which there are actually more of, the typical turn-off time is 140 microseconds. So there's a lot of those off times. So I'm going to see if we can get away with going from 200 down to 150 without anything stepping on its toes. Okay, when I did that, we again got a nice little bump in our ratio there. So 1.7 to, or whatever it was, to this now. So now the thing to do is to go up to 20 volts. So I know it reads 20.3 there, but if we slow everything down, 20.01, sue me, I'm off by 1/2000. That's good enough for me. Actually, don't sue me. I don't want the headache. Please don't sue me. So now we'll get rid of the delay, run it, and see what happens here now. Okay. That's what it's bringing back to. And you can see that we're getting more than a doubling out of the secondaries despite the input voltage doubling. And that will be reflected when we put our numbers in. So I've left the timing all the same. And I'm pretty sure that it's independent of voltage, but I'm gonna diddle around and make sure of that. But that's now the ratio. There's in and there's milliwatts out. So let's take it up to 30, and then I'll diddle around with the timing, make sure the timing's still optimal, and then we're going to change the load. So here we are at 30 volts, and it's swinging back to 21.1 something, which actually percentage-wise isn't as good as at the lower voltage. It's more damped, but this is moving up faster than it should, the voltage there. So I'm going to put, I've left all the timing the same, I'll put this in for 30 volts. So that's the ratio that we have at 30 volts. And so we have this trend going on from 10 to 20 to 30. I think the trend continues. Now the problem I have right now, these Comas AC37s, they're 60 volt alternating current relays. And what I'm starting to think, because I keep frying them, is that when you go from positive 30 and it swings down to negative, 28, that's counted as 58 volts. So I keep trying to put it up to 40 volts and 50 volts, and I keep frying them. And I'm either running too much current through, or 60 volts alternating current means you get 30 volts positive to 30 volts negative. And I suspect it's the latter, but I'm running out of these. I might have one or two more. It's not like they're the perfect relays. It's just I've used them a lot, and I kind of like standardize things on them. So in other words, in this video, we're not going up to 40 or 50 volts, but there are plenty of 400 volt relays. So the thing to do would probably be to run it at 200 volts and see if this trend continues, or at least run it at, as I'm saying, I want to run it at 36 volts with the battery test. But instead of a 100 ohm load, let's do the same thing with a 1000 ohm load. So a bit more resistance. And I'm not going to go through all of them well, I probably will, but I won't film it. I'll just work it out, the timing out at 10 volts, because you don't want to mess something up and blow something up when you're at 30 volts. And we'll see what this ratio is with a little bit higher resistance load. So here I'm running it at 30 volts. And the main difference with it less loaded, it really springs back well. And so when I ran it at 10 volts, that was our ratio. And when we plug in the numbers here at 30 volts, that's our ratio of out to in, or in to out, whatever. And you know, consistent with being less loaded, the optimal timing did slow down from 700 to 750 microseconds. So I mean, this starts to be where it doesn't look as much like, well, maybe it's a measurement error. But I am kind of disappointed. I was seeing considerably better than this previously, and so this is, for me, it's sort of, there's a lot of art involved because I don't really know exactly everything that's going on. There's one thing I'm almost certain would improve it, and perhaps this is what I was using before. If we go with a 4.7, I looked at this more formally, and it improves down to about 1 UF, but a 4.7 is about all I'll be able to get a reading on here. I'm almost certain that would improve things a bit. I'm not sure how much. Now, the other questions. I'm starting to think that, you know, the other E-cores that I have are a little bit larger. That might help. You might want a little bit larger air gap. You don't want too large an air gap because, as I said, when I just made an infinite air gap, it didn't seem to want to transfer out to the secondaries. But the main thing that I think, let's get this thing out of the way. The main thing I'm thinking, I mean, right now it looks like I might even have more winds on the primary than I have on the secondaries. You know, I realize that this isn't, you know, your standard AC turns ratio thing going on, but the turns ratio is still important, and you might want to get some of that flyback transformer stuff going on. So in other words, if I take some winds off here, it will transform voltage better. And I want to nail that down, that can you just keep removing winds here, because they'll probably, like everything else with this, there'll probably be a sweet spot, but can you just get away with removing winds to change the turns ratio and not make things worse, and ideally make things better, at least up to a point. Because the other thing here, I mean, you know, we're putting in 147 milliwatts, and that's out. It'd be nice to actually be putting like a watt in or 2 watts in, and you do that by getting rid of some of these winds to let it run faster. So I don't know, I'm going to work on that now, and I'll either use that to end the video, or that'll be the start of the next video. So let me just work on that, and especially if it improves things, I'll probably throw it on the end of this video. But this is enough to test it with some nickel metal hydride 9-volt rechargeables and just see, because you know the other question when you're going batteries to batteries, of course you're not going to have a resistor in, but what, you know, the idea here is you could run, as I was saying, say 4 9-volts, 36 volts in, and then run it to 2 9-volts on one side, 2 9-volts on the other side. And it would probably be, if you put the 2 in parallel, then that would probably be like similar to having a 1,000 ohm load. And if you put them where you're going from 36 volts down to 18, I'm sorry, the 9 volts would be like a 100 ohm load. The 18 would be closer to a 1,000 ohm load. And if you really, I might do this, if you really wanted to try and nail it down, you could look at the waveform with 100 and 1,000 ohm load, look at the waveform when it's going into a battery, you know, to try and match it to something like this. I've never looked at it with like a 10K ohm load, but at that point it's going to be I don't know what it would do, but this is good enough. And this is good enough to go with the batteries, but I'm going to work on it more. And as I said, I'll either update you here or in the next video. Okay, now we're cooking with gas. So I just went to a different set of E-cores here, and the windings are better, the inductances are matched better on the two secondaries. It's thicker wire here, blah blah blah. I don't really know what's going on. This is actually a bigger air gap. Bigger air gap, but now you got a turns ratio between the primary and your secondary. There's more lines on the secondary. To make a long story short, when you plug everything in, we're at 10 volts, and that's our ratio now between milliwatts in, milliwatts out. Let's take her up to 30 volts. Well, one step forward and 1/4 step forward. I mean, it's better than at 10 volts, but it's not the big jump I mean, each of these is its own animal. And I don't know exactly, like I said, it's like an art. But we're moving in the right direction. I would have liked to have seen 2 for the ratio, but that's out and that's in. I'm going to fiddle around with a few more things, and then I'm going to end this. This is a good place to wrap it up. But this is, this is with that circuit that I showed how to build in the last video, and with a couple E-cores, it's better to have a little bit of an air gap that you can get that kind of ratio of in to out. So I'll confirm that with some 9-volt batteries, and then maybe buy a solid state relay that handles 5 times as much power, and you have something where you're able to run a cell phone and your laptop or something like that, or at least like keep them charged in an emergency. But I'll be looking for better ways to do this that are less unpredictable and less finicky, and ideally that have a much better ratio. I think this one will be unpredictable and finicky, but will have a much better ratio if I had to guess. I have no idea what the Tom Bearden thing is going to show. And then, can you get to doing this same idea of breaking the lens effect away from the primary when you're drawing power off of a secondary? Can you do that without a core? And that would be really cool if you could. So those are the things that will be worked on going forward. Thank you for your time. Stay healthy, and talk to you later. Bye.